Okay, hello members of the jury. Thanks for participating in my graduation defense today. My name is Liang, a joint training PhD student by UMass and the Tianjin University of Technology. My doctoral project is experimental development of air-stable magnesium-based nanocomposite materials for hydrogen storage. The promoters are Professor Ronnie Snyders, Professor Mingbang Chen, and Professor Wenjiang Li. I will introduce the presentation from four aspects: introduction, objective of the work, experimental strategy, result, fossil fuels, and global warming. The picture shows the growth of population and the development of industrial. The exploitation of fossil fuels is increasing. The large-scale use of fossil fuels results in large number of pollutant gas emissions. As you can see in the figure, year by year, the greenhouse gas emissions has caused global temperature rise. The global warming has become a hot issue. Regard those pictures, we can find the emission of CO2 related to ice and the snow melting, sea level rise, threatening human survival. At the same time, also cause a lot of environmental damage, such as soil, water pollution, and so on. So for the fossil energies, the figure represents the combustion of fossil energy has led to a large amount of CO2 emissions, and it presents a sharp rise in global temperature. By 2300, the planet can be too hot for human life. The import of fossil fuels is increasing recent years. From fossil fuel statistics, countries all over the world are facing the problem of excessive use of fossil fuels, resulting in the shortage of fossil fuels and serious environmental pollution. Therefore, if we want to keep the sustainable development of industry and nature, it is necessary to explore clean new energy. Renewable energies are more and more developed. As well now, clean energy such as water energy, wind energy, solar energy, hydrogen energy, and so on, they are rich in reserves, clean and environment friendly, and can be used sustainably. They are good for human beings and nature. Regarding some reporters, we find many countries have put in forward objectives of the development for clean energy, encouraged to invest the new energy. The figure on the right, we can find the investment of new energy are increasing from 2004 to 2019. The utilization of new energy are accelerating. And until 2019, the global investment in new energy will be $28.2 billion. H2, the hydrogen as an efficient energy vector. As well now, the demand of electricity in electrical-based market would be by far too high because it needs energy vector that can be used out of the electrical grid. It is difficult to build a large number of charging stations and recycle waste batteries. Recent studies also show that hydrogen cars could be a solution for the future. And hydrogen energy vehicles represent low cost, mainly from water conversion, eliminating the problem of waste battery conversion. The hydrogen cars are therefore likely the future. In the H2 fuel cells picture on the right, as clean energy vector, H2 can generate electricity during fuel cell operations. The water vapor is only exhaust. So facing the fossil fuels problem, we indeed need to use hydrogen as an energy vector that can be stored because of the production of green energy. So hydrogen vigorous cycle since many years. H2 is considered as a promising energy vector that could facilitate the fossil fuels-based switch towards sustainable energy systems. Indeed, refer to picture on the left about the H2 cycling. We can find H2 can be produced by various electrochemical and biological methods. Also has a higher chemical energy, clean production, and sustainable since water is again by the fuel cell. However, before H2 used as fuel economically, the issues related to its production, transportation, and storage must be solved, especially because of H2 has large volume, making the storage of hydrogen is not safe. That restricted the development and the utilization of H2. H2 storage options. When considering the use of H2 energy in the transportation industry, the most important obstacle to the future hydrogen economy is lack of safe, efficient, and economical vehicle hydrogen storage. And from the left picture, we could find by comparing the different storage methods of hydrogen, H2 stored in gas need high pressure, and liquid hydrogen needs low temperature, while solid H2 storage materials have a great application perspective because of their higher density and safety. So, commonly used solid H2 storage materials were metals and alloys, which are shown in the table on the right. MG system, especially MG system, represent a higher capacity, but most of the metal and alloys hydrides have large metal density. This resulting in a very low mass percentage content of hydrogen, generally only 2% to 5%. Nowadays, strong efforts are developed to design materials able to store H2, raise high storage density, mild operating conditions, fast absorption, desorption, and good recycling properties in order to enhance the hydrogen utilization. Could MG hydride be as the best choice? Table in the left represents the hydrogen capacity of various systems. We could find the capacity of MG H2 could reach to 7.6%. In addition to magnesium has rich reserves, low cost, high density. So MG hydride has a good perspective as hydrogen storage material. But for MG hydride, its thermodynamic and kinetic behavior should be improved, and MG can easily be oxidized. This would lead to poor cycle performance. Facing the problem of thermodynamic and kinetic performance, the commonly used solution use the catalyst and preparing nanosized material. However, the catalyst just could improve the kinetic property, but have no obvious effect on the thermodynamic properties, and also involved complex operation process. But for nanosized solution, refer to the picture on the right. This solution could achieve high surface area, more active states, and short diffusing. Refer to the figure we also could find. By decrease the size, the reaction substitution energy is decreased. It could overcome the thermodynamic stability of MgH2 system. So nanosize is an efficiency solution to improve the property. Mg has high reactive towards oxygen. The reported material such as Mg nanoparticles PMA is an air-stable nanocomposite. Regards the images, The nano-mg particles are uniformly dispersed in polymer. Its thermodynamic and kinetic properties are improved, but involves using of unsafe organic Mg, as well as the handling storage performance of the material still cannot meet the requirements of U.S. Department of Energy and the vehicle application. So based on the research and the background, we made the objective of the work. Considering the development of Mg-based nanocomposite for handling storage applications, also very promising. Those materials do not yet reach the necessary performance to fulfill the standard of U.S. Department of Energy. The technological processes that are used to design those materials often employ chemicals that can impact the environment. Therefore, in this work, our primary objective is synthesis using clean synthesis rules, new polymer Mg nanocomposite materials that would be efficient as hydrogen storage material. Experimental strategy. Use industrial technology to develop air-stable Mg-based nanocomposite and explore their hydrogen storage properties. Part 1 compares the reported PMA Mg nanoparticles composite. We use safe organic Mg by wet chemistry approach to propel the air-stable PMA Mg nanoparticles. We call it PMC. And multi-word carbon nanotubes PMA Mg nanoparticles, we call it MPMC. Part 2. Use environmental-friendly plasma-based approach by magnetosphering and plasma polymerization to propel air-stable Mg plasma polymer composite C-film. Those propelled samples, their handling storage properties also will be studied. For the wet chemistry approach, the synthesis and H2 storage property of Mg-based nanocomposite, PMC and MPMC, all samples are synthesized in an argon-filled glower box. The reaction scheme for the synthesis of PMC and MPMC composite. Safe organic Mg is mostly used as a precursor. In laboratory, the propelled lithium nicely used as a reducing agent to reduce the organic Mg. The uniformly dispersed Mg nanoparticles were directly reduced in PMA. The precise parameter will explore the influence of reducing agent and PMA. The carbon nanotubes on the size of Mg nanoparticles, and the H2 storage performance of the samples are tested through the gas-solid H2 storage test system. Part 2. Plasma-based approach to propel the Mg-CH nanocomposite, including 2 steps: the synthesis of Mg nanowires by magnetosphering and glass, and the synthesis of Mg-CH nanocomposite. The CH layer is propelled to cover the Mg nanowires C-film for protecting it from oxidation. Considering the poor thermodynamic H2 storage properties of C-film materials, we propelled the nanostructured Mg. The nano-Mg C-film is deposited by magnetosphering combined with glassing angle. The Mg target was placed on the top of the device. The silicon was used as a substrate. Below the Mg target, fixed at a certain angle with the target. Based on the shadowing effect, there was no atom deposition in the shadow area. So the Tito colonel Mg were propelled. Nanostructured Mg could be achieved. Plasma polymer coating. We have developed a plasma polymer coating to protect the nanostructured Mg from oxidation. In same reactor, ethylene used as precursor. In IF power system, sparking the proxol and many fragmentations and radicals is spattered in the chamber. Then the plasma polyethylene thin film is synthesized by PCVD to cover the Mg nanowires and protect them against oxidation. In the right picture, we present the preparation process of Mg-based nanocomposite. The plasma polymer is grown on the nanostructure Mg before venting. Many fragments and free radicals are deposited on the surface of the nano-Mg vial and grow. The conformal deposition of a plasma polymer protective coating to avoid corrosion of the nanostructure Mg. Result: the synthesis of PMC by white chemistry approaches the characterization of the composite synthesis mechanism H2 storage test. PMC experimental parameters. The results are shown in the table. With increasing of PMA, the diameter of Mg nanoparticles is decreased. The PMA has an effect on limiting and decreasing the size of Mg nanoparticles. The optimal parameters is the ratio of organic Mg to PMA is 3 to 0.5. Regards the TM images, Mg nanoparticles show regular shape. And we also can find the Mg nanoparticles were uniformly dispersed in PMA. The Mg nanoparticles are stable towards oxygen and refer to the diameter distribution figure of Mg nanoparticles. Its average diameter is about 5 nanometer. And the constitution and oxidation refer to XRD spectrum of PMC. We could find the composite PMC put in air for 30 days. There's no MgO and Mg hydroxide. But refer to the spectrum of pure Mg, put the pure Mg in air for 3 days. They could find strong diffraction peaks of MgO and Mg hydroxide. We also find the diameter of Mg of blending the composite is similar to the pure Mg. Regard those analysis results, we conclude the synthesized mechanism and modeling. First, the organic Mg ion are diffused to PMA solution and it activates a recollate ion of MMA by the electrostatic attraction. And then the reduced Mg nanoparticles are dispersed in PMA solution by lysine the reduced agent, and coordinates the oxygen atoms of PMA to form a PMA molecular layer on the surface of Mg nanoparticles. Finally, the Mg nanoparticles are dispersed in power structure PMA. For the composite H2 storage performance of PMC, refer to the non-isomer H2 absorption-desorption curves. Compare with pure Mg, the PMC has lower absorption-desorption temperature. And the composite absorption peak is nasal. That could explain that PMC has fast absorption speed. Refer to the isomer high-pressure H2 absorption curves. And 200 degree, the PMC shows a faster H2 desorption within 20 bar. And when increasing the pressure to 80 bar, the H2 absorption amount is 4.25%. After 30 days in the air, the PMC still has same H2 absorption performance with the synthesized PMC. So next, the H2 absorption kinetic test. We also measure the PMC's absorption kinetic. Refer to the curves and the condition 200 degrees 30 bar. Result catalyst aging PMC would absorb 4.8% H2 and show rapid absorption rate within 8 minutes. And refer to the second figure regards the curves. PMC could release 4.15% H2 and 270 degrees, which show more excellent H2 desorption amount than the reported MG-PMA composite. And refer to the suction curve cycling present, the PMC also present stable H2 absorption, desorption, recycling. In order to further reduce the size of Mg nanoparticles to improve its thermodynamic and kinetic properties, the carbon nanotubes were added, propelled MPMC, the composite, including the characterization of composite and the synthesis mechanism. The composite MPMC refer to the distribution of Mg nanoparticles. The Mg nanoparticles have an average diameter of about 3.6 nanometer. It refer to the T images. It can be observed from the pictures that Mg nanoparticles has lattice regions of 0.3 nanometer and 0.286 nanometer, which is consistent with that of 101 and 002 Mg. So regards the TM images, the Mg nanoparticles were uniformly dispersed in the template. In addition, the existence of other byproducts in composite was not observed in the energy spectrum. The synthesized mechanism of MPMC. First, the carbon nanotubes were dispersed with soluble PMA, and the Mg ion initially was attracted to the template, and then the Mg ion were reduced on the template by the lithium nazzling. Finally, the template prevents the reduced Mg nanoparticles from aggregating with each other. Nanostructured MgC films by magnetospherin and GLAD, including the study of the growth mechanism impact of oxidation. The chemical composition of the film. In order to measure the composition, chemical composition of the MgC film, we use SPS to measure the chemical composition of the dense Mg. Refer to the SPS spectrum for a deposited film that reveals the presence of element of MgOC. It appears that the Mg line is composite by two components, metallic Mg and Mg ion. And then we use argon spatula the C film. After 2 minutes of sparring, the depth is about 40 nanometer. The MgO peak completely disappeared, while the peak intensity of Mg strongly increased. So both those observations clearly confirm that the deposited film is only oxidized on the top of surface of the film. Suggesting MgC films have been propelled successfully. Turning the morphology the theta angle, we fix the substrate pressure at 0.26. And in the figure, the substrate angle increased from 0 to 89. We could find the deposit angle strongly depends on substrate angle. And this also could be achieved before to the cross-section images of Mg. This can be explained the influence of the atomic shattering effects during deposition in GLAD, in particular, and the substrate angle greater than 60, the shattering mechanism is strongly enhanced. and result in porous columns towards the web source. And the titer of column keep stable when the substrate angle greater than 85. For in fact, from the images, we can see for the substrate angle is 80, the columns already has a well separated. The impact of oxidation, we have shown that Mg films easily oxidized even during the growth, which impact of the morphology. We have intentionally introduced oxygen during the growth, mixture 95% argon and 5% oxygen to study the phenomena. Refer to the composition, chemistry composition. When there's no oxygen in sparing device, the oxidation reaction also takes place on the surface of the MgC film. This could be explained as oxidation during transfer of the test sample. And refer to the second figure. When the amount of oxygen increased to 5%, the oxidation takes place during the sparing and the deposition process to obtain the MgC film. Even just a small amount of oxygen will have a significant impact on the composition of the film. The morphology evolution. The picture on the left shows the cross-section images of the nano-MgC films when the oxygen content increased from 0 to 5%. The morphology of the sample is strongly affected. With increase of oxygen content, the column is smaller, and the column width and spacing are greatly reduced. The tilt angle is stable, and the column length is slightly changed, as well as the intercolumnar space by 50% and even 60% when considering the higher content in oxygen. So it is therefore necessary to develop an integrated solution to protect our non-structured C films from oxidation. The first part, the MgCH nanocomposite by plasma-based approach, including synthesis of the plasma polymer coating and the design of the composite material. Develop a plasma polymer to protect Mg. In order to protect the MgC film, we develop a plasma polymer to protect the C film. A mental sparing device shown in the right picture. On the silicon substrate, argon is used as a sputtering gas to propel nano-Mg, and then plasma polyethylene is deposited on the surface of nano-MgC film. The efficiency of plasma polymer barrier coating is correlated with the cross-linking density of the material, and the cross-linking density also affects its mechanical properties. Some possible conditions should be considered. In our work, we prepared the C film is used as H2 storage material, so the C film cross-linking density should be considered. It is related to the gas diffusing, has to be high enough to reduce the diffusing of the gas through the coating, and then to protect nano-MgC film. In addition to the cross-linking density of the coating is related to its internal stress, should not be too high because it must be avoid the generation of cracks in the coating correlated with the mechanical properties of the material. The evolution of the barrier properties. The barrier properties of the plasma polymer ethylene layer have been indirectly measured through their capacity to protect aluminum from corrosion. By the corrosion resistance analysis. through the electric chemical corrosion test of the coating and uncoated samples, the electrochemical impedance spectra was obtained. The figures, the result shown in the figure on the right. So first figure presents the bell substrate. It put in solution for 7 days. Refer to the low frequency model show various corrosion. And refer to the second figure. This is we use the sparing the worker power 20 to prepare the plasma polymer ethylene layer and is used to cover the alumina substrate. And after immersion for 7 days, the first figure and the second figure compared, we could find compare with the uncoated alumina substrate, the low frequency, the second, the 20 power propelled layer to cover the substrate aluminum shows better anti-corrosion performance. So the 20 paired CH plasma polymer film significantly improves the barrier properties of the substrate. And however, refer to third figure. The 100 work power propelled the coating to cover the alumina substrate. It has low frequency impedance value, is similar to that of the bell substrate. So this phenomenon can be considered as high internal stress, which makes the coating crack in the solution. So for the 100 work power propelled CH layer, there's no impulse of corrosion resistance. The evolution of the mechanical property, as shown in the figure on the left, the hardness and the Younger modulus of the coating were increased with the F power increasing, and the change trend is same. It can be explained that the mechanical properties are also determined by the degree of cross-linking polymerization. So thus, the deposition is higher, the degree of cross-linking polymerization is higher. The figure on the right shows the change of deposition rate with the work power. With the increase of power, the deposition rate of the CH coating increased linearly from 5 nanometer per minute to 22.7 nanometer per minute, which can be explained as increased power leads to more particle collision. More free radicals are produced during the collision process, and the deposition rate of coating increase. This side update allows to understand that because of a higher fragmentation level of the precursor with work power, the deposition rate as well as cross-linking and the hardness and the Younger modulus increase as well. The design of the Mg plasma polymer film composite. Based on our study, in order to grow a plasma polymer ethylene film presenting good barrier properties onto the nanostructured Mg films, it is necessary to use a relatively low F power in order to avoid the appearance of cracks and delamination in the material. Therefore, a power of 20 has been used to demonstrate the concept. Then in the same reaction chamber, the plasma polyethylene coating was deposited on the surface of the nano MgC film. And when the deposit time increased 9 minutes, the top of the magnesium column along a length of about 200 nanometer was covered by a CH layer, and the weight of column was observed to increase from 200 nanometer to 300 nanometer. When the deposition time is increased to 20 minutes, the whole nano column will be covered. and the thickness of the coating will gradually decrease from top to bottom. According to those stage, under our experimental conditions, it will take at least 10 minutes to obtain a reliable coating to protect MG from oxidation. For high enough deposition duration, conformal deposition of the MG-based nanocolumns by the plasma polymer is observed. So, before to the research and our work, the conclusion: L-stable nano MG polymers composite were prepared by both white chemistry and plasma-based technologies. The white chemistry synthesized composite MG-PMA can absorb 4.8% of H2 within 8 minutes and release 4.15% H2 at 270 degrees. This is attributed to the small size of the MG particles. In addition, this material is stable towards oxidation for 30 days, the minimum, and adding multi-word carbon nanotubes to the system allow to even reduce the size of the MG particles. The composite can absorb 6.8% of H2 within 20 minutes and reveal rapid H2 absorption-desorption rate. The nano MgC film is prepared by mantle and glass. The growth and morphology depend on the deposition angle and the sparring. It shows that it is necessary to protect those C films from oxidation. A plasma polymer anti-corrosion barrier coating has been developed from ethylene in the same deposition chamber. It is shown that its composition, mechanical properties, and corrosion resistance can be controlled by adjusting the deposition power. The coating prepared at 20 power represents the best corrosion resistance because of its adapted mechanical properties. The acknowledgement: I would like to thank Professor Ronnie Snyder's, Professor Minfang Chen, and Professor Wenjiang Li for their valuable opinions and guidance on my experiment. Thank my classmates and my good friends for their support and encouragement during my study. Thanks to the members of the jury who participated in the review of this thesis and attending the defense. So, thank you for your attention.
Nous, présidents, secrétaires et membres du jury, chargés de conférer le grade académique concerné, déclarant que Liang, né à Anhui, en Chine, le 14 juillet 1988, a obtenu en l'année académique 2019-2020 le grade académique de docteur en sciences. It means that you are awarded a doctoral degree in science from Mons. Congratulations, Uwe.
Thanks.
Congratulations for that. Yes, in principle, you should be with us and sign this degree here, your degree. But what we will do is that we will sign it, and Ronnie will send it to you so that you can sign it.
Okay, thanks.
Okay, we will take care of that. Congratulations from the whole committee. It was very nice. Yes, that would be nice. Maybe if you can share the photograph you just took, because it would be nice for us here in Mons. We have a tradition is that after each ceremony, PhD ceremony, there is a group picture with the candidate and with the committee members. And so that's just what you did. You take a group picture of you with us, as I understand, with this screenshot. So if you could send it to Ronnie, for instance, if you allow us to put it on the Facebook page of the chemistry department, as it is for all the thesis. But sorry, I was interrupted. I would like to congratulate you, Uwe, for the beautiful work you did. It was beautiful because it was jointly between two very different countries with two different approaches in chemistry on one side, in physics. But it was difficult, of course, also because of that. But you went through very nicely with very nice results, with a number of papers. And on behalf of the committee, I would like to congratulate you already. And then now I will simply give the speech to your promoters, to Ronnie and Professor Chen and Professor Li, who also would like to say a few words. Ronnie, please.
Yes. So, of course, we first of all, I would like to congratulate you for the finalization of your PhD work. It has been a long adventure that has started a few years ago when I visited TUT with our previous president of university. It was in the context of a royal king visit in China. And then during this visit, I met Professor Liang Li, and we just discussed together during the lunch, and we decided to try to do something together. And a few months later, we had the opportunity to start a co-share PhD, and you were the candidate that has been chosen by Yang. And because of it, you had the opportunity to come in Belgium, I think for the first time for you, and to enjoy the European way of life. I think you visit a lot during your stay in Belgium. You visit the entire Europe almost, and you had very good time in our country. Except of the touristic part, I really enjoy to see you work in the group. I think you did a lot. As already mentioned many times, you almost did 2 PhD work, because one in China, one in Belgium. So it was not an easy situation, especially because you also discover a new lab, new colleagues, and a new way of life. And you did it well. You succeed to do it. So congratulations for that. Just to finish, I also want to congratulate you because the thesis is very important, of course, but I think that in the next few days you will have another very important accomplishment because you are close to the end of your presidency. So this is a second good news that is coming for you. So it's really nice. I think you will have a very nice summer in China, taking care of the new baby and as a doctor.
Thanks.
So congratulations, Rui.
Thanks, Professor.
Thank you, Ronnie. Now I would like to ask Professor Li and Professor Chen to say a few words.
Okay. Today, the Liang Hui finished his PhD degree defense. First of all, I congratulate her. At the same time, I appreciate to Professor Lonnie's side. Thank you for hard work during these years. And thank you, Professor Li. Thank you, the chairmen.
Thank you. Thank you very much. Thank you
and
very much.
Other professors and Professor Li. Yeah, in the future, I hope the professors in Mons University and Professor Li to visit our university in the future. Thank you very much.
Thank you for the invitation. Thank you. Professor Li, yes, please.
So finally, time is so fast. In last 4 years, I think it's worth for Hui to did a lot of work and then to write several nice paper. So I think this is very good experience for you. and it's very, very important for you in your future. In last 4 years, you spent 2 years in Belgium. It's very nice country, and you from your there, you have learned many things. You have know so many good professors. I think this very important and very good experience for you. Actually, I want to see you are international PhD students. So later, I think you will be have a very good future, and I hope you can keep touching with these professors and always tell us some of your good news to us.
Okay.
Thank you.
And secondly, I like to thank you, Professor Ronnie Snyders and Mons University. I have visited Mons 2 times in last 4 years, and very nice experience, and see a very good environment. So for me, I think is very good things, and I hope we can keep our cooperation later. And after the disease pandemics, I think the world will open again, and I hope we have some good opportunities to visit each other in the future. Thank you, Chairman.
Thank you.
Thanks, Liang.
Thank you very much. Okay, what I would like to do to finish, to conclude, is to thank and to congratulate her again on behalf of all of us.
Thanks.
Thank you and congratulations. And I wish you the best for your future, and first, of course, for the baby to come. And then I would like to thank also all the members of the committee for having this thesis presentation and discussion today. Usually at this stage, I invite the people to go for a drink, all together. But okay, so just enjoy your drink wherever you are. Just now, let's go and enjoy a drink. Okay, thank you very much.
Thanks to everybody.
Bye-bye.
Okay.
Thank you. Bye-bye. Congratulations. Bye.